Step into the Coliseum of Cambridge exams. Look around. Thousands of students enter this exact arena every single year. But only the truly prepared, the ones who have absolutely dialed in their exam technique, walk away with top marks. Welcome to the explainer that will serve as your ultimate insider's blueprint. Today, we are mastering the Cambridge AS and A-level Computer Science syllabus 9618, specifically targeting one of the most rigorous battlegrounds they can throw to, the client-server model of networked computers. Whether you're building foundational network knowledge of the IGCSE levels, like syllabus code 0417, 0478, 0983, 0984, or 2210, or you're tackling the heavy advanced requirements of our main focus today, 9618, the Coliseum rules are the same. But before we get to the advanced A-level material, let me paint a picture of a real past paper scenario, specifically a classic question from the 9713 code vault. Imagine a dynamic split screen right now. We have two students, Alex and Sam. When asked to explain how a web browser accesses the page using the client-server model, Alex totally panics and overloads the answer with raw facts. He writes, the client is a computer, the server is a computer, they connect, HTTP is used. There's absolutely no analysis of the TCP/IP stack, no layer breakdown, just a desperate data dump. Sam, on the other hand, rushes, completely misses the command word requirements, and casually writes, the client asks for a web page, and the server gives it back. Both of these students just lost massive points. It's a bloodbath of red pen marks. Alex didn't analyze, and Sam missed the technical depth entirely. In this explainer, we are going to look at exactly how to avoid their fatal mistakes and transform flawed reasoning into top-tier A-star answers.
Okay, let's dive into this because this quote right here sets the entire stage for our strategy. The difference between a B and an A-star in computer science often comes down to how well you understand the client-server model. That is a direct, unfiltered observation from a senior Cambridge examiner. Think about that for a second. The stakes are incredibly high. This topic isn't just some tiny footnote you can skim over the night before. It is the absolute backbone of modern networked computing. It tests your understanding of protocols, data transmission, security, and algorithmic efficiency all at once. Examiners use this topic as the ultimate filter to separate the good students from the great ones. They are looking for a conceptual mastery that goes far beyond simply memorizing definitions from a textbook. They want to see you navigate the complexities of request-response cycles, packet switching, and load balancing with absolute surgical precision. If you can conquer this, you can conquer the paper.
So here is our tactical roadmap for today. First, we'll cover core principles. Second, we'll break down the method mark strategy. And finally, we'll dive into the highly classified examiner warnings. We are going to deconstruct, solve, and evaluate everything needed for maximum points. Let's get moving.
Section 1. Core Principles. Understanding the cognitive domains. Let's establish the unbreakable theoretical foundation you need to survive.
Listen closely. To win the game, you have to know the rules. And the rules of the Cambridge 9618 exam are strictly dictated by assessment objectives, or AOs. You can't just walk in and write what you know, you have to write what they are measuring. The assessment objectives for the client-server model are split across 3 distinct cognitive domains. First step, knowledge and understanding. This is your baseline ability to recall facts, like precisely defining the role of a file server versus a web server. Next is application. This is taking that raw knowledge and applying it to a completely novel scenario, like explaining how the client-server model functions specifically within a local area network for a highly secure hospital database. Finally, we have analysis. This is the absolute highest tier. This is where you evaluate, compare, and break down complex systems to show how different components, like routers, switches, and load balancers, interact to minimize latency and prevent bottlenecks. To hit all 3 of these domains perfectly, you need a structured framework. We call it the PEAL framework: point, evidence, explanation, link. Top students make their point, provide technical evidence like specific protocols, explain the architecture and context, and link it back to the question's exact parameters. Before we continue, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Let's look at the difference in action. A standard student relies entirely on the rote memorization of core principles. They try to brute force their way to a good grade by simply remembering what a router is or what an IP address does. But the Cambridge syllabus emphasizes that a top performer exhibits connected, conceptual understanding that is completely transferable to unfamiliar contexts. They don't just define a router, they evaluate a router's efficiency in handling concurrent HTTP requests in a high-traffic client-server topology. They decode the command words flawlessly. If the question says evaluate, they know they need to give pros, cons, and a justified conclusion about the network setup. If it says describe, they know they need to state specific technical characteristics. Now, I want you to imagine a 30-second timer ticking down in your head right now. Think about the PEAL framework I just mentioned. If I ask you to evaluate the use of a proxy server, a standard answer just says it hides your IP. A PEAL answer says, point, a proxy server enhances security. Evidence. It acts as an intermediary for requests from clients seeking resources from other servers. Explanation. This prevents direct external access to the internal network, mitigating DDoS attacks. Link. Therefore, in a corporate client-server setup, it is vital for maintaining uptime. That is how you secure maximum points.
Section 2. Methodology and the method mark strategy. Let's see how to secure points even when multi-step calculations get incredibly tough. In computer science, particularly in the advanced 9618 syllabus, you are frequently dealing with algorithmic thinking, binary extractions, and complex network calculations. As this quote highlights, marks are awarded for the process. When you are looking at data interpretation skills, for example, if you are asked to extract network IDs from binary representations to determine a subnet mask, or perform intricate network capacity and bandwidth calculations, showing your step-by-step decomposition is absolutely critical. The examiner wants to see your brain on the page. Imagine we are doing a live rewrite right now of Alex and Sam from earlier. They're changing their red pen marks to green check marks. Why? Because they are finally showing they're working. If you make a tiny, silly arithmetic error right at the very end of a massive bandwidth calculation, but your underlying logic regarding packet switching and bit rates is flawless, the method mark strategy ensures you still get the vast majority of the points. Never, ever just write the final answer. You are leaving free marks on the table.
And this brings us to the exact 5-step procedural framework for problem solving that guarantees those method marks. We call it the Deconstruct, Solve, Evaluate method. Step 1. Identify given information. Literally highlight the constraints in the question, like the total payload size and the available bandwidth. Step 2. Break into logical steps. Use algorithmic thinking to outline the transmission sequence before you even touch a calculator. Step 3. Solve systematically. Run the calculation for transmission time, showing every single conversion from bytes to bits. Step 4. Check for reasonableness. Look at your answer. Does a 5 terabyte download over a 56 kilobit connection taking 3 seconds make any logical sense? Absolutely not. Catch your own mistakes. Check your math. Step 5. Make justified recommendations on how to optimize that client-server transmission. This is the blueprint. Apply this and your marks will skyrocket. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's move into an interactive workshop space right now. I want you to imagine a complex data chart showing server request loads over time. You have a 60-second mental countdown to extract the core trend. When analyzing algorithm quality for server loads, you have to identify time complexity using Big O notation. How long does the server take to respond as requests scale from 100 to a million? Is it linear? Is it exponential? Next, identify space complexity. How much RAM is the server application consuming to maintain thousands of concurrent TCP connections? Then, you must check edge cases. What happens when 0 clients connect? Does the system crash? What happens when a DDoS attack simulates 10,000 clients connecting simultaneously? Does the load balancer fail over correctly? And finally, analyze the effect on overall network performance. Higher-order assessment objectives demand that you evaluate these alternatives and provide justified recommendations. If you can critically analyze a flawed pseudocode snippet for a server connection and instantly spot the missing boundary condition, you are thinking like an A-star student. Section 3. Examiner Warnings. It is time to open up the highly classified principals report. I am stepping in as your trusted mentor here, giving you the restricted insider intel straight from the Cambridge Principal Examiner reports. These reports are essentially the examiners practically begging students to stop making the exact same mistakes year after year. I want you to genuinely think about this for a second. Where do you think students lose the most marks when discussing the client-server model? Is it forgetting the obscure protocols? Is it getting the math wrong on subnetting? I want you to anticipate the traps before we reveal them. If you know exactly where the landmines are buried in the arena, you won't step on them. Let's see if you guessed correctly. Let's break down the top 3 fatal mistakes candidates make, which block them from the top grade boundaries. Mistake number 1, confusing cause and effect. Students often state that a slow network is caused by the server simply being far away, rather than explaining the technical reality of increased latency due to multiple packet hops, propagation delay, and router processing times. Mistake number 2, forgetting boundary conditions and edge cases in their algorithms. When writing pseudocode for server handling requests, candidates completely forget to program what happens when the connection drops mid-transfer during a TCP handshake. Mistake number 3, and listen to me, this is the biggest one by far. Answers are not specific to the context given.
If the question asks about a hospital's client-server network and your answer just talks about general internet browsing without ever mentioning secure patient data access, API encryption, doctors or hospital wards, you lose every single application mark. You must anchor your theory to the specific context they give you.
Examiner alert. The principal examiner reports reveal that candidates consistently and disastrously confuse key terminology. You absolutely cannot use words like memory and storage interchangeably when discussing server architecture. You cannot confuse a switch with a router or a client with a general node without losing clarity and marks. You must clearly define terms before using them in your extended responses. Let's do a 30-second speed writing challenge right now. Try to formulate a perfect paragraph defining a web API in a client-server context using our Peel framework. Point: an API allows communication. Evidence: it uses protocols like HTTP or REST. Explanation: it defines the methods and data formats allowing the client to securely interact with the server's backend database without exposing the raw database itself. Link: this is essential for a weather app on a client device pulling real-time data from a meteorological server. If your terminology is weak, your whole algorithmic implementation crumbles. Precision is your best weapon.
Let's move to a highly practical tool before we reveal the final success system. Here is an actionable memory hack derived straight from top-performing students. Create your own mnemonic using the first letters of key client-server terms to anchor your knowledge before exam day. For example, to remember the lifecycle of a request, connect, request, process, respond, terminate. CRPRT. Make up a bizarre phrase that sticks in your mind. Cats, read papers, reading times. Whatever works for you. Now, let's lock in the complete computer science answering system. 3 rules that guarantee top marks. Rule 1. Command word decoding. Always identify if you need to describe, explain, or evaluate. Rule 2. The Peel framework application. Never write a paragraph without point, evidence, explanation, and link. Rule 3. The time management matrix. Calculate 1 mark as 1 minute of writing and always plan for 20% review time at the end to check those edge cases. Students who implement these computer science strategies see an average improvement of 2 whole grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.
So, I leave you with this final provocative thought to take with you out of the arena. How will you adapt your algorithmic thinking to ensure your next client-server response hits absolutely every single evaluation requirement for that A-star? You now have the ultimate insider blueprint. You know the exact technical pitfalls the examiners are hunting for. You know the frameworks to structure your logic. Now it is entirely up to you to apply it systematically to your own analysis. Don't just read the textbook, interrogate the systems. Keep analyzing, keep optimizing your technique, and I will see you in the next explainer.